We're talking about noise monitoring, and our guest today is the chairman of the IARU Region 1 EMC Noise Monitoring Group, David Lauder, G0SNO. And David, welcome and thank you very much for making the time available and talking about this important subject.
Okay. Well, thank you, Hans, for organising this event. So what we're going to talk about today is the IARU Background Noise Measurement Campaign. And why is noise important? Why do we want to measure it? So, look at okay, scrub that, start again.
It's all right, you start.
The trouble with a screen share is that there's 2 Microsoft PowerPoints to share. Oh, there's a one, show me in front of the presentation. Right, so we want to scrub this and start again.
Whenever you're ready.
Got the right, yeah, there was a button that said show me in front of the presentation, and I clicked that and went funny. Right, okay, sorry, we'll start again.
No, you get going.
Right, okay then. Okay, so this noise measurement campaign started some years ago, and I'll tell you about it and why it's useful. So why did it start? Why did the IARU Region 1 start a background noise measuring campaign? And then we're going to talk about what is RF noise, how does it affect communications, why is it important for radio amateurs to be aware of RF noise, how can we measure increases in RF noise level, why is it important to monitor noise, why should I join the IARU EMC Noise Monitoring Group, and conclusions. Okay, so why was the campaign started? So this was the IARU Region 1 General Conference in 2017 at Landshut in Germany. And the Norwegian National Society presented a paper, proposal for this noise measurement campaign, which was accepted. And the idea was that individual members of the IARU member societies can measure noise and report the results in an easy way without elaborate test equipment. So that was approved, and now I'm going to tell you about what's happened since. So this was the actual wording of the recommendation. Start a simple noise measuring campaign amongst Region 1 member societies. So we haven't restricted to Region 1, and we've got some board. And to have an independent opinion of the noise situation in the bands and trends over time. So is it increasing? We think it is. evidence of that. So it actually runs for 5 years, the collection, data collection. And so we started off by collecting information from existing projects and understanding what had been done. So anyway, next step, what is RF noise? Well, you could define RF noise as any unwanted signal. And we need to think about what do we need to do with an electronic communication system. So we have to get enough power from the transmitter to the receiver so that we can recover the wanted signal. So how much is enough power? How much is sufficient signal at the receiver? So we need to think about the signal to noise ratio. So that is signal power divided by noise power. And they'll be in linear units of power like watts or microwatts or picowatts or whatever you want, as long as they're both the same. And signal to noise ratio is what we need. It needs to be good enough. And to find it, we need to know the signal power and the noise power. Well, how much signal power we get to a remote point, this is pretty well understood in all applications, not just amateur radio. So we've got some gains, possibly transmitting antenna gain and receiving antenna gain. And we've got some losses. We've got free space path. We might have excess atmospheric loss at microwave frequencies. We might have fading, multipath. We might have polarization loss if our transmit and receive antenna polarization isn't perfectly aligned. And we certainly would have losses in feeder cables. So when you put all that, you can pull that into a link budget and you can come up and say, this is how much power we can get to the receiver. So that's the signal, but what about the noise? Well, let's think first of all about a satellite communication system. Now I'm thinking now of a microwave frequency where we've got a dish antenna pointing up into the sky. So there is some sky noise, which consists of cosmic noise, atmospheric noise, and ground noise. There is some receiver noise. And there might be some man-made noise or interference. But if we've got a directional antenna pointing up into the sky, that's probably insignificant. However, most of our communication systems are terrestrial, and there are additional man-made sources of noise and interference. And this would include, for example, many amateur satellite receivers, like on a VHF, where you've got your antenna is not highly directional pointing up, right? So it will see ground-based sources of noise and interference. But in any case, these would include DARC ignition systems in vehicles. This is that's what kicked off the whole EMC standards movement, really, was when cars, early days of radio, cars driving around with spark ignition making crackles on your radio. Done about that was high voltage electricity transmission lines, corona discharge, and then electric motors with brushes and commutators. So they are well-known sources of interference, big or small. Electric drills, food mixers, sort of thing. Switches and thermostats, just a click, but significant. But the big one that has come in recent years, switching power supplies. So instead of having a nice 50 or 60 hertz transformer, which can be quite big and heavy, you have a switching power supply that switches at maybe 50 kilohertz with a smaller transformer and a larger amount of RF interference. So everything you use has probably got a switching power supply: a computer, a monitor, a TV set, a battery charger for a phone mobile phone battery, a battery charger for a laptop computer, a battery charger for an electric vehicle. They're all switching power supplies. LED lighting. LEDs run about 3 volts, so you got to transform the mains voltage down, usually to about 10 or 30 volts. They have chains of them in series, but that's a switching power supply. And then electric vehicles, you have variable speed DC motor drive that works by pulse width modulating, and heat pumps for air source heat pumps, ground source heat pumps for that matter. Some of them have variable speed AC motor drives, which involve chopping up the mains with high-powered electronics. Solar PV systems generate DC, and then you have inverters to the AC mains. And another twist to the solar PV story is that sometimes the panels have individual optimizers, which are switching DC to DC converters, and we do have some problems with these. But anyway, so those are some additional man-made sources of interference. Others. Now, how much noise is there? So we've looked at what the sources of noise are. How do we measure it, or how do we quantify it? We'll start with thermal noise. So the electrical signals are carried by electrons, and these have random movement, which depends on absolute temperature. So there is a equation that the noise power is KTB. We'll go into that in detail, but that is the fundamental limit of any communication. The smallest signal you can detect is limited by thermal noise and possibly other sources. If you're only limited by thermal noise, then you're doing well. There's sky noise, which includes cosmic noise from outside the Earth, outside the solar system, atmospheric noise from the atmosphere, and ground noise from the ground, which is warm compared to the sky. If you're thinking about satellite communications, sky is cold, ground's warm. So ground is noisier. You don't want ground in your antenna beam width. Now, sky noise is often specified as a temperature, and it depends on frequency. And below 100 megahertz, it increases substantially. All this has been studied in great detail and published in an ITUR recommendation, P372. So this covers the frequency range from 0.1 hertz to 100 gigahertz. Now, of course, you don't have many operations on 0.1 hertz, but there we are. If you wanted to, then that will tell you what the noise levels are. So they're expressed in dB above KTB. It's not possibly very easy to interpret. Explained how to do it, but this can be converted to sky noise temperature. So that tells you natural and man-made noise levels, and of particular interest is the man-made noise levels. So what it tells us is it has different environmental categories: rural, residential, city. In fact, there's 4. There's quiet rural, residential, and city. So if you add the man-made noise to the natural noise, this will tell you the total noise that you will need to take account of in your communication system. So how does RF noise affect communication? Quite simply, if you've got too much noise, then your signal-to-noise ratio is not good enough, and no communication is possible. So, if you need to improve the signal-to-noise ratio, what could you do? You could increase the transmitted power, or reduce the received noise power, or both. So the important thing about signal to noise ratio is that it's the ratio that matters. So it's signal power relative to noise power. So if, for example, man-made noise had increased by 3 dB due to increasing amounts of sources, then to get the same signal-to-noise ratio, we would need to increase the transmitted power by 3 dB, so that would mean double the power if we want to maintain the same signal-to-noise ratio. Now that is fundamentally true of all forms of radio communication, not only amateur radio, everything else, broadcasting, mobile phones, whatever. If you increase the noise power, for example, man-made noise, then you've either got to increase your transmitter power or reduce range of your communications. Well, increasing the transmitter power is very often not an option because you're regulated by licensing, and typically you might be running at the maximum power permitted by the license. So if you can't increase the transmitter power, then you're a bit stuck because your noise is going to be affecting, as I mentioned, affecting your communications. Even if you can increase the transmitter power, you need more electrical power into the transmitter. And if everybody's transmitter power has to increase across the world because of rising levels of background noise, then that has an environmental impact for the extra energy used. And in another context, man-made RF noise could be regarded as a form of environmental pollution of the electromagnetic environment, which is less well known than the real environment, but nevertheless, I regard it as a form of environmental pollution. And I regard it as particularly unfortunate that a number of recent developments that are improving the environment by reducing energy consumption are actually polluting the electromagnetic environment, specifically LED lighting or poorly designed LED lighting. Anyway, that's how it affects. Why is it important for radio amateurs to be aware of RF noise? Well, you've got noise on your receiver. Is it all natural noise? If it is, you're lucky if you're in a quiet rural location. But if you're anywhere in a built-up area, it's likely that some or most of your RF noise is from man-made sources. So, how much man-made noise have you got, and how does it compare with the levels in IARU P372-16? We're on to 16, version 16 now, that's just come out. But the levels are the same as they were on -14, except it's now presented much better. So, if the RF noise is higher than the P372 levels, how could you reduce it? Well, you might be able to identify a source, or more than one source, a predominant source that is increasing the noise. You might be able to check the EMC compliance of that source with whatever regulations are affecting your area. You might be able to apply mitigating measures like ferrite rings if it's something that you own yourself, and you might report it to the authorities for investigation. So that's why it's useful to know about RF noise rather than just regard it like a spell of bad weather that you can't do anything about. Think, well, maybe we can do something about it. See, if you've got a source that is 30 dB over the limit, that's equivalent to 1,000 sources that are at the limit. So if you can root out one or two major sources of noise, you might well be able to get major improvement. So, how can we measure increases in RF noise? So this is what the noise measurement campaign is all about, is to say, is the RF noise level, background noise level, increasing? And if so, by how much? So the starting point has to be, what is the existing RF noise level, or what was it when it was measured? So as I mentioned, this has all been studied very thoroughly by ITUR 372-16. And of that range, 0.1 hertz to 1000 gigahertz, the current range of interest is 50 kilohertz to 31 megahertz. But we are hoping to extend this into the 50, 70 and 144 megahertz amateur bands, but we're concentrating on up to 31 megahertz first. Reason for 31 rather than 30. Now, the P372-16 data is based on measurements made very many years ago, and most in the 1960s. So is it still valid? And how can we find out? And if it isn't valid, are the implications of that? Well, you see, it has been suggested by manufacturers of devices that are not very EMC friendly, shall we say, that man-made noise has increased in recent years due to proliferation of electronic devices such as switching, power supplies and LED lights. Well, has it? Well, we're about to find out. But regardless of whether it has or not, there is pressure in some quarters to relax the EMC standards on the grounds that if the background noise levels have risen and are higher than shown in P372-16, then what's the point of having strict EMC standards? You might as well relax them, and if there's a lot of noise, we'll make even more noise. Well, that is being argued in some quarters. Powerline communications being a case in point. Oh, I forgot to mention that. So, what the noise measurement campaign set out to do is to make data available to IARU with independent and up-to-date measurements of current radio noise levels, particularly in the amateur bands, and show how these are changing with time. So this can provide support for the view that EMC standards need to be tightened, not relaxed, because if there's a lot of noise due to proliferation of electronic devices, then we need to reduce the amount of emission from each device. As you can imagine, manufacturers wouldn't be too keen on that idea because they don't like the standards they've got already. One particular point is the number of devices. The current standards are based on the assumption that there is only one device causing interference. It's 10 meters from the victim receiver, and you're only receiving broadcast signals, not like amateur radio. Now, of course, the one device assumption is clearly not valid anymore, and much work is being done in EMC standards committees to address this. So, next thing, if we're going to measure noise, what do we need to do? So the noise measuring campaign group agreed at the start that this is what we needed to do. Number one, make automated measurements. So, computer sitting there, scanning across the bands, logging the results. Distinguish between noise and intentional transmissions. This is another thing that has led to some misunderstanding. We've seen reports from people who've said, oh, well, you look at there's so much noise on HF, and they're confusing noise with intentional radio transmissions. So what we're doing is we are separating out the intentional radio transmissions and looking for the quiet spots in between. Now, very important is make measurements in such a way that they can be compared to the methods used in ITOR 337214. It was 14 at the time. And that is basically a short vertical antenna at ground level. So that's what we use. Use an antenna that can be calibrated. So an antenna where you can relate the output of the antenna to the RF field strength in volts per meter. Then you can compare your results at different locations. And most important, you can compare them to the ITUR curves. And then collect all the data, store it in the server. So that was what we set out to do. And it has been done. So the first outcome is from the German National Society, the DARC, and they call their system ENAMS, Electrical Noise Area Measuring System. So it achieves all those 5 objectives, and it does it in a way that is compatible with the ITUR 37216, which is important because we want these results to be accepted by EMC standards making organizations and say to them, look, this is what is really happening to the noise floor. And if we go to them with any sort of, measurements made with amateur antennas and receivers and it's S9 here, they will say, well, we can't really relate that to the 7216 levels. So that's why the DARC have done something very well engineered and accurate and will be accepted by standards making organizations. So we're going to look at some example output from this system. So most of the stations are in Germany. There's about 50 odd in Germany and a few in other countries, Austria, Belgium, Switzerland, New Zealand, US and UK, one or two in each. So there's a link there where you can go to look at any of the plots from any of the stations. I'm going to show you some from the ENAMS system UK 181. Now, we have a particular challenge in the UK, especially to the north of London, which is that we have strong medium wave broadcast transmitters, whereas in Germany, all the medium wave broadcasting is closed down. So they don't have some problems with overloading like we do. I've got a notch filter operating on this UK 181 system, and this is to prevent overloading. And at the moment, the field strengths are not calibrated between about 500 kilohertz and 2 megahertz. So you will see a little notch in the frequency spectrum, and this will be calibrated out because we are working on a calibration factor that will flatten it off. But at the moment, that is to be noted. So this is the spectrum plot. So this is the raw output. It's gone along from 50 kilohertz to 31 megahertz because interesting things sometimes happen just above 30, like things start to come up. And the two frequencies, the two colors, are 2.75 kilohertz, which is comparable to amateur SSB bandwidth, and 9.15 kilohertz, significance of 9 kilohertz is that EMC standards use a 9 kilohertz measurement bandwidth. So you can see that the different bandwidth doesn't make any difference to the peaks of the intentional signals carriers, but it does make a difference to the noise floor. So the noise floor is an imaginary line. You see the mouse moving there? Imaginary line that we draw along the bottom of all of the orange lines. Well, it's actually a little bit more to it than that, because what we want to do is find quiet frequencies. Now, if you've ever looked for quiet frequencies, you'll know that finding a quiet frequency, a truly quiet frequency with 9 kilohertz bandwidth, there would be hardly any. 2.4 kilohertz, there aren't many. But if you go down to 300 hertz bandwidth, like you've used for CW, then you can find quiet frequencies where the noise that you measure is the background noise level on the band due to natural noise, man-made noise, and distant signals where long-distance propagation is taking place. So that's an example spectrum plot, and as I mentioned, that dip there isn't really there. Now, what it does is it goes through and does a noise floor plot. So for the noise floor plot, you've taken out, as far as possible, the intentional signals. So you'll notice the intentional signals, you see they're all narrowband carriers. Well, I've got some modulation on, but they're predominantly the narrow band. So it goes through and takes all that out and says, now this is the noise floor. And it does this every hour throughout the day, 24 hours a day, 7 days a week. So here's an example from 19th of March, from 1800 to 2300 UTC. And that, as I mentioned, ignore that notch. I call it the bathtub filter. So really, it's below 2 megahertz isn't valid. And the previous one, the spectrum plot, is presented in terms of field strength, dB microvolts per meter. That means decibels relative to 1 microvolt per meter. So 0 dB microvolts per meter is 1 microvolt per meter. And that's a level that we can approach and not difficult to get below it on those bandwidths. However, on this plot, the field strength is dB above ITUR rural. So the ITUR has it has 4 environment classes for man-made noise. It has quiet rural, which we're not showing here, rural, residential, and city. So if you were at a rural location, you would expect your noise floor to be down on this 0 dB line. Now the level goes, it's not flat with frequency, it tilts, but the tilt has been taken into account. So this is dB above rural, and it's a very good way to present the noise floor. Compare it. So the 5 dB line is residential, and the 10 dB line is city. So you can see at this location, we're mostly at city, although it's a residential location. It's not a city location. And there are a few interesting things to notice. First of all, look what's happened at 10 megahertz. The 10 megahertz emitter band is completely buried in 5, 10, 15, 20, nearly 20 dB above the rural noise, ITUR rural level. And all of that is because of VDSL, which is a broadband communications technology, which is used in the UK, that uses existing copper pairs and pushes them right up to sort of 12 megahertz, and it leaks out and makes a terrible mess. And amateur bands could be notched and should be notched, but they're not in the UK. And anyway, so that's the VDSL up to 12 megahertz. And then up here, up at, above 25, we have the neighbours' LED lighting. So they've got some sort of string of decorative LED lights around the window, not just for Christmas. And look what a mess they make when you can tell what time they switch them on. You see, 2200 they're on, 2300 they're on, but not so. Maybe they dimmed them there, and then the rest of the time they're off. So that's the noise floor plot. That really is the core output from the ENAMS system. Also does a heat map. Not quite sure why there's a gap in that. That's not expected. But what the heat map shows us is we've got time along the horizontal axis. We've got frequency from 0 to 31 megahertz vertically. And then the color tells us the number of dB above rural. So you see blue's quiet, green's noisy, amber's very noisy, red is extremely noisy. So you can see, for example, up here, that at 21:30, there's the LED lights come on, and it sort of stays on until nearly midnight. But and then some of these things, like that little blue thing at 25 megahertz, that's caused by power line telecommunications, which is notched in the amateur bands. Some of the amateur bands, anyway. So that's the heat map plot. So those are the three plots that it gives us. Now, how can you measure your own noise? So these DARC systems, there's a limited number have been produced, and there's not going to be any more. And so the next stage is to be able to measure your own noise. That was the original objective. So, for example, SARL in South Africa is producing a system using Raspberry Pi computers and PRs. So these won't be as accurate as the ENAMS measurements, because the DARC have taken great trouble to make sure everything's calibrated and measurement uncertainties are really low. Nevertheless, still a very useful way to get. You can assess the noise level at your QTH, compare it with noise levels at other locations, compare it with the ENAMS plots as a reference. And this will tell you, have you possibly got a local noise source, possibly a non-compliant electronic item? So why is it important to monitor noise? What can it tell you if you keep an eye on it? Well, you can assess the impact, or IARU can assess the impact of man-made noise and interference sources, especially switching power supplies, we've already mentioned, switching power supplies in LED lighting, switching power supplies in variable speed motor drives for electric vehicles, switching power supplies in AC motor drives, heat pumps, inverters in solar PV systems. These are all relatively recent innovations, and they all have implications for appearance. Optimizers and solar PV systems. What could we do? We could report suspected non-compliant devices to the relevant authorities, because if we don't report them, nobody else will. Manufacturers not going to report themselves. And if the relevant authorities say they haven't had any complaints, then there's pressure to relax the EMC standards. Oh, we don't need the standard as tight as this, there's no complaints. Well, we need to show that there are complaints. And feed data into the EMC standards making process. Reasons that I've already explained. Why should you join the IARU EMC noise measurement? Well, you could measure your own noise, identify sources. Is there something excessive? Is there possibly one or two things that you could deal with that will then give you a great improvement? Are there things which are suspected non-compliant? What can you do if it's your own equipment in your own house, or even maybe a neighbour that you're on friendly terms with? You might be able to apply some mitigating measures, or it rings somewhere. Then you could report it to the authorities. Just make sure that they do get some complaints.